All right, use substitution. This bad boy is sort of like, it's like the chain rule of integration. It's that thing that everyone has trouble with. It's the thing that causes people to call me when they need, they finally like bite the bullet and get a tutor when they get to this, because it's, even if you can kind of like make it through the rest of calculus, this tends to be the thing that throws people under the bus and they throw up their hands. Anyway, it's not super bad, but we will have a lot of long videos in this chapter because it is such a confusing topic. Now, I want to show you though that it's pretty much the chain rule. So this particular video, we're going to kind of work a couple of examples towards the end, but just to sort of get you used to the idea of use substitution and sort of tell you what the heck's happening. That's what this video is all about. The next one is going to be sort of showing you a sort of straightforward, reasonable way to do it. Because what happens is there's different ways as far as like mathiness or the amount of sort of algebra you have to write down. Teachers really vary a lot. And some, it seems like, especially lately, some teachers have been using this very sort of mathy, ugly way of doing it that makes it make no sense at all. It's sort of a plug and chug thing, except it totally takes all the logic out of it. So the approach I'm going to be taking is to sort of look at this as the chain rule in reverse, and we'll sort of be basing this video and the next video a little bit on the chain rule. And in the next video, I'll show you sort of the straightforward way to where you show enough work to get full credit from almost every teacher, but at the same time, it actually makes a little bit of sense what you're doing. All right, so what is use substitution? Well, I want to take you back for a second to the chain rule and remind you that when we first learned derivatives, there was actually, we started with x and then we moved on to u. So before you had the chain rule, if you want to take the derivative of something like cosine of x, that was just sine x, right? The only problem was, and that worked great, and all the formulas you had were all, they had x's in them, d over dx, x, that kind of thing, and then x on the right. Then we introduced a chain rule, because the problem was that in this situation you could only take the derivative of cosine of x, or cosine of p, or cosine of t. As soon as you got to something like cosine of 2x, whoops, you couldn't integrate that, right? You were just hosed. But that's what the chain rule took care of. The chain rule said, hey, you know what? Let's just call 2x u, so let's just say, hey, u equals 2x. And then when we take the derivative of cosine, we're going to get negative sine of that same u. But then we have to sort of make up for the fact that we sort of did this little substitution. We're going to throw in a u prime on the end, right? So that's where the 2 came from. So if we're taking the derivative of cosine of 2x, we end up with negative 2 sine of 2x. But the point is, by doing that u substitution, it allowed us to do the sine and cosine derivatives and power derivatives and stuff, power rules on things other than just x. And what happened to the formulas was they went from all x's to all u's. So if you look up here, on the left, I've got all the rules we've been using to this point in integrals, and they just have x's in them. X, dx. Occasionally we have an n, like for the exponent or something, but the only variable we have on the left side of these things is x. So x all day long. But now with use substitution, just like with the chain rule, we're going to be able to integrate a lot more stuff. So like a little thing like 2x won't throw us off anymore the way it would have in integrals in previous videos. However, it's going to get a little bit harder as a result, right? But if you look at this, we've got the same formulas. Instead of x to the n, we've got u to the n. Instead of dx, we got du. And then on the right side, everything changes too. So instead of x to the n plus 1, we've got u to the n plus 1. But the formula is exactly the same. So what we're going to be doing with use substitution is just showing, we have to like show our work and sort of this process of picking something to be u and then all that stuff. It's going to be trickier on these than it was on the chain rule. A little bit more work, but it can be pretty much equally straightforward. All right, so that's an overview. Let's take a look at the chain rule specifically and how this kind of wacky stuff works. So if start you off with just taking the derivative. If we just took the derivative of this stuff on the left side, so x squared minus 1 to the 4th power over 4. If you just did the chain rule derivative, you would end up with this on the right side. So I'm not going to do that right now. I mean, we just take the old power, move it out front, and then that 4 would cancel this 4, and end up with x squared minus 1 to a new power of 3. Okay, so that's, we use the power rule, except the chain rule caused this 2x. So this right here is our u prime, this 2x, because that's the derivative of what the power was of, right? So if you want to pause the video right now and take the derivative of this thing on the left and make sure it actually equals this thing on the right, go for it. But I just want to, that's how it works. So the derivative of this is this. So where this 2x came from was the chain rule. But now I want you to think about how integrals and derivatives are opposites. That's why some people call the integral the antiderivative. So what I'm saying is that if this was the derivative, if this over here is the derivative of this, then that means that the integral of this must be this stuff. So that's what I've written down here. All I've done is taken this stuff right here and just put that behind an integral sign right there. And we said that, hey, if all this stuff is a derivative of this stuff, then that means that the integral of this stuff must just be the backwards process, and that takes us right back to the left again to get this. We've already talked about where plus c comes from and everything, and that's not going to change. We still need a plus c, even with u sub. But the point is that if you look at this integral more closely, I'm going to get rid of some of these lines for a second. If you look at this integral more closely, what happened to this 2x? So like if you just walked up this integral and we hadn't just had this discussion and you didn't see what this integrates to, then you might look at this and say, well gosh, this looks like a power rule. So it makes sense that my u would be x squared minus 1 or whatever. So since that's the third power, maybe if I integrate it, I can just add 1 to the power and divide by the new power and use the power rule. But what happened to the 2x? I have a 2x right here, and I do not have a 2x or anything resembling it over here. It's like the 2x just up and vanished. What the heck? Well, it turns out that's how u substitution works. Because the chain rule sort of created a 2x out of nothing when we took the derivative. When we do the opposite chain rule, when we integrate, that 2x is going to unvanish, or sort of vanish after having materialized from nothing. So it came out of nowhere here, but then when we integrate and go the other way, it's going to vanish again, and we'll just get back to the original thing we had on the left over here. So this is messy. We'll do this with a couple more functions, but the point is that some stuff's going to vanish. So when you integrate with u substitution, you're not going to integrate everything on the left. Some stuff is just going to vanish into thin air as you integrate. And that sounds really weird, except hasn't that been happening all along? Like if I integrated x squared before, you know, I integrated x squared dx, and that would just be x cubed over 3 plus c, naturally. But what happened to dx? I don't know. It's just part of the integral sign. So the integral sign and dx both, you know, just vanished into thin air when we integrated. And that's all that's happening now, only instead of just dx vanishing into thin air, we're also going to lose our 2x or whatever else is part of our du. So in the next video we'll get into how to do this step by step, but I just want to make the point that, you know, it seems like what students find the most confusing is that some stuff just vanishes into thin air and doesn't get integrated. But really it's just part of the reverse chain rule process. And stuff's always going to disappear when you integrate. It's just a question of how much stuff. Alright, so here's a similar problem, only with a sine, you know, derivative of sines. But the derivative of sine is just cosine of 3x, right? So derivative of sine of 3x is cosine 3x. And then because of the chain rule, we have this times 3 here. Because if we did the chain rule on this, our u would equal 3x. And therefore our u prime, that's part of the chain rule, would just be 3. So that's where this 3 came from. But of course, just like with the last problem, if this is the derivative of this, that means that this must be the integral of this. Which is to say, if I integrate cosine of x times 3 dx, I should get just the sine of 3x, which is what I started with. You'll notice once again some stuff went bye-bye. The 3 right here does not appear anywhere over here. There's no 3 in front, there's no 3 behind. The 3 just up and poofed into midair along with the dx and the integral sign. But that's because the 3 was part of that chain rule junk. So, as you can see, some stuff's disappearing. And last one we'll look at real quick in this particular mode. Here we got an exponential. When you take the derivative of an exponential, this would be your u, right? The whole exponent up here is your u. Which means that when we take the derivative of this with a chain rule, sure, we're just left with the same exponential, and we got this 2x plus 3, which is just the derivative of that exponent. That's just our u prime. Which means that when we integrate this whole hunk of junk, we're just going to end up with this again. So when you integrate e to the x squared plus 3x times 2x plus 3, this whole thing, we just get this out. So it's as if this just vanished into nothingness. What happened to it? That's what u sub's going to be all about. Alright, so something's always going to disappear. What u sub is going to do, and what the u substitution integration technique is going to do, is it's sort of like you have to dot your i's and cross your t's before you just let stuff vanish into the thin air. You got to make sure that the right thing is vanishing. So just like the chain rule tells you exactly what that u prime is going to be, you have to have u prime or you can't integrate. So I'll show you what I mean right here. So here's one, let's just say we were given this integration formula, this integration problem. Now we can guess it's a power rule because we see something raised to a power of 4. And you can kind of think of this, you can use the chain rule to help you. If instead of integrating you were going to take the derivative, it's pretty obvious that this is a chain rule problem with a power, right? So it's a power rule chain rule problem. So same thing with integration. If you see an exponent of 4, it's like 99% of the time you're going to need the power rule. And this is what the power rule for integration looks like when you're using u's. So the problem is we need du. And du is really just like u prime dx from the chain rule. It's basically just u prime. So if you want to integrate, if you want to pretend that you're integrating u to the 4th, what you've got to do is make sure that your du matches up. So basically, if you want to integrate x cubed plus 1 to the 4th power, you've got to make sure that you have the derivative of what's in the parentheses right here. So let's just double check. So step 1 we did. We said, you know what, this kind of looks like a power rule. Let's see if we can do it, because we might not be able to. So we decided to use the power rule. Step 2 is identify the formula as u. So if we're going to use the power rule, u is whatever's being raised to the exponent. So it's just whatever's under that 4 exponent. So our u in this case is x to the cubed plus 1. It does not include the exponent because in the formula, u is the thing without the exponent. So then we've got to take the derivative of u and make sure that you've got that next to the dx. So if u is x cubed plus 1, then that means that u prime, or we might call it du or whatever, is 3x squared, right? And sure enough, look at that. We just happen to have 3x squared sitting there. And of course, this is how they do these problems. It has to be contrived so that it works out. But because we have that 3x squared there, it looks like step 3 checks out. We've got the derivative of our u right there sitting next to the dx. And step 4, I didn't bother writing it, but step 4 is integrate. So now that our du's checked out and everything, we can just integrate this like we wanted to. So the integral of this puppy is just going to equal that same u, so the same stuff. And then we're going to add 1 to the power. So the exponent goes from 4 to 5. And then we got to divide by the new power, just like we always do with the power rule. And then of course there's a plus c tacked onto the end. Alright, so that probably seemed like a lot of hoopla we went through. A lot of checks and balances, a lot of dotting our I's and crossing our T's and double checking we had stuff. But that's how USub works. If you don't have the derivative of your u sitting right here, you just can't integrate, unfortunately. So there's going to be problems where you just can't integrate, which is new. That never happened with the chain rule. With the chain rule, you could always take the derivative of anything. It might have been 2 steps or 1 step or 10 steps. It could be crazy hard or crazy easy, but you could always do it. With integration, if your du and u prime and stuff don't match up with these steps, you're just hosed. You can't do that integral. So the big trick on these is usually figuring out what's your u and matching all this stuff up. That's what makes USub so tough. It can be kind of a puzzle you have to figure out instead of just grinding through the plug and chug the way you do with the chain rule. Alright, so here's another one. Let's take a crack at it. So obviously if I'm looking at sine x squared, the thing that's really sticking out to me, and this same thing would be true if I was taking the derivative of this instead of the integral, we got a sine here. So it really seems like we're going to need the sine integral formula. So I wrote that right here. Alright, so what does that mean? Well, we got to just be sure that we've got our u and our du and stuff. So it looks, if you look at the integral formula here, the u that shows up in the sine formula is whatever the sine is of. So here, if we're going to use this sine integration formula, our u has to equal x squared. We sort of don't have a choice about that. Which means our u prime, or our du, as we'll probably call it mostly when we're in this chapter, and actually from here on out, you'll be doing this for the rest of calculus, but our u prime, or our du, same thing, is just a derivative of 2x, of x squared, which is 2x. Alright, so now's when we look at the problem and make sure, hey, do I have, make sure you've got that. Make sure that you've got this 2x sitting next to the dx. Alright, so do I have a 2x sitting next to the dx right here? I don't. Really close though. I just don't quite have it. It turns out we don't have to walk away, because you notice it says if not bail. That's really, it's not quite as black and white as that. If we didn't have an x here, we'd be hosed. But actually we're just off by a constant. It's like I wish I had a 2 here. If I just had a 2 there, boy, we could integrate this thing with the sine formula that I cleverly wrote to the right here. So how can we just manufacture a 2 right there? Well, it turns out, and we've done this a lot in calculus, you can sort of, when you have a constant, you can move it anywhere you want. So what we're going to do is we're going to put a 2 there, and then to make up for it, we're going to put a 1/2 out front. 2 times 1/2 is just 1. So we haven't done anything illegal algebraically. We've just multiplied by 1. I feel like we've done this trick before. I can't quite remember exactly where. But the point is that if you want to put a 2 there, all you have to do is put a 1/2 out front, and that saves your bacon. So at this point, everything checks out, because now that I conjured this 2, I've got the 2x I needed. And now I can just integrate it using this formula on the right, because my u and my du are both, they match up. If you have an x squared for your du better be 2x dx. And believe me, we'll get tons of practice on this in later videos. So don't worry if this is going over your head a tiny bit. But point is, now we can just plug and chug through the formula. So the integral of sine u is just going to be, now that we still have a 1/2 here that we created, so we got to put that down. And then it's going to be negative cosine u, and our u is x squared, and then plus c. All right, so just distribute that in, and we got negative 1/2 cosine of x squared. All right, not so bad. Once it matches up, it's usually pretty easy to do the integral. The trick is all this, you know, annoying stuff where you got to match up your u and your du and make sure everything's going to work out. All right, last one. Got e to the 3x here. And of course, it's pretty obviously an exponential, so I want to use the exponential formula if I can. And of course, here's the exponential formula. So what is my u? My u is this little guy up here. So if I want to use the exponential formula, my u is going to be 3x, which means that my du, or my u prime thing, we're going to use these letters interchangeably, but really we're just to use du from here on out. Derivative of 3x is just 3. So that means that I've got to have a 3 in here next to the dx if I want to use u sub. So I got to conjure a 3 there. And of course, to counteract a 3, I got to put in a 1/3. That might seem like hocus pocus, but you'll get really used to doing that really fast once you do a lot of these. All right, so now I can integrate this thing at this point because it checks out. My u and my du match. So this tells me that the integral of e to the 3x is just e to the same thing. So I got to keep my 1/3 that I just conjured from nothingness. Oops, don't need an equal sign. And then we just keep our e to the 3x, just like with derivatives. The integral formula for e is the same. And there you go. All right, so if that didn't make total sense, I would highly recommend that you go and watch the next video, do some later videos, do some practice problems. This is going to become a little bit second nature, but if you ever get confused as to what the heck's going on, come back and watch this video. After you've tried a few of these and practiced it a little bit, it'll probably make more sense to you. But the main story is that because chain rule, when you take the derivative with chain rule, you end up with a bunch of extra stuff on the end of the problem, which means when you go backwards and you integrate, sort of like a reverse chain rule integration, all that stuff that you added because of chain rule has to go away. So that's the moral of the story. When you integrate, all that junk's going to go away. U sub is all about figuring out what junk do you need and what junk are you going to cross out that's going to go away when you actually do the integration.